All right, I think we can start. All right. Good afternoon, everyone. It is my great pleasure to introduce today Sanjay Deshpande. He is already known by many of us. He's a former intern in our group. Currently, he's a postdoc at Northwestern University. His expertise lies in the hardware design of cryptographic schemes. He's been focused quite a while on post-quantum schemes. And today he's going to be talking about the hardware design of this scheme called HQC, which was recently selected by NIST and the PQC standardization effort. So the floor is yours, Sanjay.
Thank you. Thanks, Patrick. And thank you for inviting me to give a talk. So this is a work that we've been doing for a while now, and there is some follow-up work in this area as well. I'll talk about both of that. So to start with, the main motivation behind this work is that modern cryptography forms the backbone of security in today's digital infrastructure. And we know that it primarily comprises of symmetric key cryptography and public key cryptography. However, the rise of quantum computing and the research towards building large-scale cryptographically relevant quantum computers can put the existing public key crypto systems that we use today at risk. Specifically, Shor's algorithm can potentially break existing pre-quantum public key crypto systems such as RSA that we use today. So we need a quantum-safe alternative, and this is where post-quantum cryptography comes into the picture. The post-quantum cryptography algorithms, they run on classical computers, just like the pre-quantum cryptographic algorithms, and are believed to be both quantum secure as well as classically secure. For a decade now, post-quantum standardization efforts are in progress around the world. Organizations such as NIST, ISO, IETF are working towards streamlining this process of standardization. And HQC, which is the focus of the talk today, belongs to the NIST standardization process. So I'd like to give a brief insight into what has been going on as part of the standardization process. So the standardization process was kicked off in 2016, and a call for proposals was made for submitting two categories of candidates: post-quantum key encapsulation mechanism schemes and post-quantum digital signature schemes. So there were 69 candidates that were admitted in round one, and then after multiple rounds of evaluation, two post-quantum key encapsulation mechanism schemes and 3 digital signature schemes were selected for standardization. And among them is HQC, or Hamming quasi-cyclic. And in parallel to that, to have more diversity in the selected algorithms, especially for digital signature schemes, another standardization effort is ongoing in parallel, and this is in its second round currently with 14 active candidates, and the evaluation is still ongoing on those. Now, when I talk about the evaluation of how these candidates are being shortlisted and selected for standardization, it relies on certain evaluation criteria. And this evaluation criteria can be broadly categorized into 3 different categories: primarily the security of the scheme, then hardware and software implementation efficiency and implementation security, and then cost. By cost, I mean key sizes, signature sizes, and so on. And this talk is going to be focused around the hardware implementation efficiency and security aspect of a key encapsulation mechanism scheme. And some more insight into the competition. So the submitted candidates to the standardization effort belong to various set of hard problems, and HQC belongs to the code-based family. Now, Another thing is like why do we need hardware implementation of cryptographic schemes? It is because it is essential in improving the security, the performance, as well as energy efficiency when these algorithms are deployed in the real world. Typically, we consider two different platforms for evaluation of cryptographic algorithms, either FPGAs or ASIC, and we evaluated our work on FPGAs. Also, evaluating and comparing hardware designs with other hardware designs or even hardware designs of other candidates is relatively complex when compared to how we compare in software. So the cryptographic hardware community sort of informally agrees on different architectures, and they are called lightweight implementations, where you try to target the area to be lower, also low in terms of energy. Then high-speed implementation, where performance is the key. Then balanced implementation to strike a balance between both of those. So with that, I'd now like to talk about, yes?
Thank you for giving the context, especially for someone. I mean, can you talk a little bit about what the actual hardware industry, because I understand they're actually also building accelerators for PQC like Intel.
Yes.
Can you map what they're doing? You obviously know a lot about them. Can you map them into this context? Like
sure. So now after standardization, basically Intel, I believe, has started putting together. So MLChem, which is the other candidate that has been standardized and the standard has been released. So they are now working towards like building an ASIC design like of that, which eventually might show up in their chip, in one of their future chips that would come out. So that we are hoping that would happen with HQC, this candidate as well eventually. Yeah. So now coming to Hamming quasi-cyclic. As I mentioned, it's a key encapsulation mechanism scheme. So brief intro to how a key encapsulation mechanism scheme works with the example of Alice and Bob. So one way this could work is that Alice can use a random seed and a key generation algorithm to generate a public and a secret key pair. Then she holds on to the secret key, publishes her public key. Bob, who now wants to initiate a conversation with Alice, would use an encapsulation algorithm and Alice's public key to generate encapsulated key and a ciphertext. He then holds on to the encapsulated key, sends the ciphertext back to Alice. Alice, on the other side, uses the decapsulation key and her secret key to decapsulate the ciphertext. And now she has a decapsulated key as well. The idea is that the encapsulated key and the decapsulated key are same. And once they have this shared secret established between them, then the further communication can happen over a secure symmetric encryption channel. Now, coming to HQC, as I mentioned, it's a code-based key encapsulation mechanism scheme. The hardness of this scheme is based on syndrome decoding hard problem. And the construction itself is based on concatenated codes. So they use two different error-correcting codes, which are shortened Reed-Solomon codes and duplicated Reed-Muller codes. And on the right is the parameter table, where I have the sizes of the encryption and decryption key, which are analogous to, say, public key and private key, and the ciphertext sizes. And the other two important parameters that we would be using today in our talk is the degree of the polynomial, that is n, and the weight of the polynomial. By weight, it means number of non-zero elements on a polynomial. Now, the way the syndrome decoding problem is set up in HQC, we see this operation repeating in pretty much all the primitives. So the way this is set up is that there are three n-degree polynomials, h, x, and y. The setup is that we have h that is sampled from a pseudo-random number generator, and x and y are these sparse polynomials with fixed weight, and these the index of where a non-zero element should appear is also generated from a PRNG. And the core operation that we see is this x plus h multiplied by y, which are polynomial multiplication and addition. The idea here is that the h and s are public values and x and y are secret. And given that h and s, finding x and y is hard. Now, taking a look into the primitives very briefly. So this is the key generation algorithm on the top, and which could be realized using this simple flow diagram on the bottom. So we have public key seed and secret key seed. So as I mentioned earlier, we sample using a PRNG, and in this case, we use a Shake 256 as the PRNG. And from secret key seed, we sample 2 fixed weight vectors, and then we perform polynomial multiplication followed by polynomial addition to generate public key and secret key. We see similar operations repeating in encapsulation as well. So we have a couple of same operations, again, polynomial multiplication and addition. And in addition to that, we have hashing as well, plus the encode where we have the read Mueller and read Solomon codes in there. Same thing in decapsulation as well. At the beginning in decapsulation, we perform a bunch of polynomial multiplication and addition. Then we perform the decode, which forms the whole decrypt operation. Following that, we do the whole re-encryption operation to make sure what has been decrypted is indeed correct. So all in all, like when trying to implement this stuff on hardware, the first thing that we do is to profile and identify the bottlenecks of the design. And what we identified in terms of a performance bottleneck was the polynomial multiplication unit across different primitives, and that contributes around 70 to 80% of clock cycles around different parameter sets or different security levels. And in terms of side channel analysis, then there are different places that we could mount the target is basically where we are dealing with secret key. So it could be the place where in secret key generation process, or in terms of decapsulation, it could be the decryption step at the beginning. So I'll talk a bit about both, one example with the side channel attack target and one for the performance bottleneck as well. So firstly, I'll talk about fixed weight vector generation process. So a fixed weight vector in the HQC is a binary vector containing a sequence of zeros and ones with fixed number of ones on a large polynomial. The algorithm that was proposed as part of the round 3 specification for this is represented with this diagram here. So you initialize a PRNG with a seed. Then there are so on each cycle you draw n bits from the PRNG, and you perform certain checks like threshold check and duplicate check. And then you populate that specific value as a 1 on this large polynomial on that index. Now the issue with this is that the 2 conditions, that is that we call rejection sampling here, has a non-constant time behavior, and this was exploited by Guo et al.'s work, and they demonstrated a timing attack on the software reference implementation of the fixed weight vector generation on the decapsulation. And they were able to recover part of the secret key with this. So to fix this, we propose an implementation trick, sort of. So we draw. The process is similar here as well. We initialize the PRNG, but we draw more than what is required in advance and store that in a memory. In terms of hardware design, it could be a block RAM. Then we go through the entire memory. Even if we achieve enough weight, we still iterate over the entire memory considering the worst case scenario. And once we get the weight, we just mask and we write zeros to the polynomial. That's the idea. And in this case, the caveat is that like if you run out of the additional bits generated, then that would still leak some timing information. So we parameterize the amount of bits that we generate in addition. So if you select a larger value for that parameter, then the probability of like design running into timing issues would be lower. But as we were working on this in parallel to that, there was also parallel work in terms of fixing this at the algorithmic level. So one of the co-authors from the HQC scheme published this work. It's called constant weight word method. So the way this method works is that each time that we draw a set of random bits from the PRNG, it is reduced to a different field. That is to avoid the problem with the threshold check. And once they get once they draw all the random bits, they put them in an array, and then a duplicate check is performed on them. Now, in case the duplicate is found in this array, then that specific position where you find the duplicate is replaced by where the address on where the array has been, where an array that specific index has been stored. So that way they solve the issue with the duplicate check. So this was recommended by the HQC team as part of the updated specification later on. However, this method has a small bias because each time that we are replacing one of the element from the indices, it is always below the value of the weight because it has to be from that range of 0 to whatever the weight is, or weight minus 1. But as the specification claims that this bias doesn't affect the security of the scheme on the whole. So we implement both in our hardware design. And just to give some comparison, the method that I described earlier, which we call fast and non-biased method, is much faster in terms of the overall time taken to compute each fixed weight vector when compared to the constant weight word. But again, it comes at a possibility that it might fail to behave constant time. So yeah. So that's how we fix the timing issue. Next, coming to the performance bottleneck, that is the polynomial multiplication. Typically, if we have A and B as two polynomials, then we have a school book technique of multiplying these polynomials using this equation that I have for Cx here, which has the overall complexity of big O of n square. But since the n value is significantly large, as shown in the table here, it could lead to like performance bottlenecks. So lucky for us that there have been some works in this area on optimizing polynomial multiplication. There are techniques like schoolbook from Karatsuba that reduces the complexity of schoolbook down to n power 1.585. So that's good amount of improvement already. And then there is more generalized method that is Tumcook. We get even lower to the complexity. And just looking between Karatsuba and Tumcook as well, it's also significant improvement already because the value of n is large. And at this point, we look at this and we see, like, should we just go for Tumcook or can we do better? Turns out the answer is yes, because one of the inputs to the polynomial multiplication is always a sparse vector. So, and it is of fixed weight. So we could leverage this information to design a sparse multiplication that could be faster than the classical techniques that we have. So the way this works is that we shift the non-sparse polynomial using the indices of the sparse polynomial, and then we perform addition for until we finish the whole weight through the array. And this further lowers the complexity to n multiplied by w, because the w value is small. We are able to achieve improvement further even from Tumcook. The cycles here assume that there is only one multiplication unit, and that could be scaled if we have more multipliers running in parallel.
As you increase the security level,
the improvement goes down, yes.
Goes down, right?
Yeah.
Is that because the sparsity also goes down?
Yeah, a little bit, yes. That's right. and the polynomial size is larger and sparsity is also lesser in that case. So, yeah. So the way that we realize it on hardware is that we start with emulating the multiplication using this variable shifter or rotation unit. We use, as I mentioned, we use the indices to from the sparse polynomial to shift the non-sparse polynomial. Then all the operations here are happening in the field x power n minus 1. So we need to reduce the multiplication result. So since it's of this form x power n minus 1, we could just fold the polynomial and then just perform addition to get it back into the field. And since we are operating in a F2 in HQC, so the additions are just XORs. So that's another nice optimization that we could achieve. Overall, by doing this interleaved reduction, we get away without storing that 2n size polynomial because as we are doing the multiplication, we just keep reducing and then accumulating the value. So this way we are able to achieve reduction in area and both memory utilization as well. Now, the actual implementation itself, we will not be able to implement such a wide shifter or have such wide registers to implement this. And we would run out of all the resources on FPGA. So we take more of a sequential approach where we parameterize the number of bits that we want to shift in each cycle with a performance parameter that usually would scale the overall design, like the memory width as well as the overall area utilization. And we could see that like as we increase the value of the shifter, the amount of time taken lowers, but the area increases. So yeah, that's one of the ways how we fix the performance bottleneck. And now one of the
So you load the polynomials into the DRAM or
the block RAM on chip.
the block RAM?
Yeah. So it's the value that I represent in n is since it's a binary. So the polynomial is in F2. So each represent 1 bit. So it's not a lot of yeah. So yeah.
So one thing I didn't understand, is your W fixed for hardware?
Yeah.
Okay.
So one natural question that arises when we talk about polynomial multiplication is, can we do NTT or FFT style multiplication for HQC as well? Probably because the popularity of the lattice-based schemes. So the problem here is that we cannot directly apply the NTT style multiplication to the binary field polynomial because it requires a finite field with special roots of unity. However, there were some works, I think there was a work in 2021 by Chen et al. Who proposed a workaround for that, and they call this work Frobenius additive FFTs. And this was also implemented on hardware by RAS et al. Last year. Briefly explaining how this works is that we start with the polynomials in F2, and then we have to convert the basis and raise the basis to 2 power m. And then the newer basis of the polynomial is called Cantor basis. Then we start with the FFT encoding, followed by the butterflies, and then we get to the best part, which is the element-wise multiplications, and then the reverse of all the operations. Now, just to give you some insight into the overhead that comparing it to our design, these both are hardware designs. You could see that the overhead of all the additional operations apart from the multiplication is significantly large. So yeah, that's one of the key bottlenecks, like why we can't use entity style multiplication for HQC. And one of the selling points was from this work was basically that we ensure constant time behavior because having this variable shifter style multiplication on CPU, there is a possibility that there could be a timing leakage. So so this was one of the selling points for them. But when we implement on hardware, we have verified this experimentally that there is no timing leakage for the multiplier.
In the original work, they observed a similar performance when they analyze.
So in the original work, they use a combination of Karatsuba and Tumkuk, the reference implementation that has been provided from HQC team.
Okay.
Yeah.
But it's like compared with the usual sparse multiplication.
The specification has one line saying that they don't opt for sparse because there is a chance of leakage, timing leakage.
Oh, I see.
Because based on the index, the polynomial would be stored in, I believe, in chunks of 64. So based on the selection of the index, then it has to, the address selection needs to happen, and that might lead to, the way the CPU is designed, that might lead to some timing information. So, so yeah, that is the reason. So now putting together these modules to form key generation, encapsulation, and decapsulation. So firstly, the key generation, we combine the fixed weight vector module and polynomial multiplication module to realize the key generation. And to give you some insight into the cycles when compared to the optimized implementation in software that uses tricks like AVX instructions and so on, we get good amount of speed up in terms of cycles, but obviously in terms of frequency, we are using a small FPGA device, and the comparison is with a high-end CPU here. Similarly, in terms of encapsulation, in encapsulation we provide two variants. One is just using one polynomial multiplication unit, and the other one uses two polynomial multiplication unit because they are independent polynomial multiplication operations. So we call them, one is a balanced approach and the other one as high speed, and both these approaches you could see are significantly faster when compared to the existing high speed CPU implementation.
So I suppose in the high-end Intel CPU, they now have this support for fields, binary fields, right? So,
Yeah.
so now
they
get
leverage
that
on
additional acceleration.
Yeah.
Okay.
And then same thing with decapsulation as well, since decapsulation uses the whole encapsulation operation. So we have two variants here as well, balanced and high speed. We get good speed up in this case as well. Now, following our work, there has been some follow-up work in terms of hardware implementations as well. These are realized as a joint design where you share as many modules as you can among all three primitives like key generation, encapsulation, and decapsulation. And the module would be able to do any primitive that we want. The first work was released in terms of hardware implementation was from the HQC team themselves. So they use a high-level synthesis design, basically converting the high-level language implementation that they have into hardware. But the performance is not that great when compared to like a hand-optimized design. Then another implementation following our implementation was released. This is hardware-software co-design, where the hardware part implements this sparse multiplication, but it is on the hardware side. So they have this. They lose a lot of performance in terms of moving data from CPU side to the programmable logic side and back. So that's why we see some performance deterioration in there. And more recently, there was another work which sort of combines all three parameter sets into one, like one design at runtime. So that's why their area is a bit higher. But overall, if we look at the time area product, it is still very comparable to our design. And also to give some insight into the Frobenius additive FFT-based design. So yeah, it's significant overhead in terms of both time and area, and the time area product as well. But one additional thing about that specific work was that it combines both HQC and MLChem in one, because they have this FFT style implementation. So they use these butterflies to also realize the lattice-based crypto candidate as well.
But by that cost, we can actually put together
Two
different architectures and still be
yeah,
better.
that is true. So
can I ask a question on that? Thank you. So is anyone looking at a metric that would measure how forward proof the hardware is? Like, suppose something comes up and people say, oh, I have to double my W, or I have to blah, blah, blah. So if you know, some of these might have better way of adapting themselves to changes than others. Is there a metric like that as to how, you know, because these things, we don't know how secure these algorithms are.
yeah.
And things might pop up, and hardware takes a long time to replace them.
True. Yeah, that's a good question. So, in terms of like, for example, weight was the
was one of the
one of
questions,
the examples, right? So, such parameters are usually added as a parameter that you could change at compile time. So, and the design adapts according to that change. So, all the bit widths and the performance of the design will adapt based on this change. Even with respect to the size of the polynomial, if that changes, the design will adapt accordingly. And most of the designs today are take this into account when they are implemented.
And also, I think that kind of flexibility that you're asking for is precisely why we have different parameter sets, right? It's like if someone kills level 1 in an attack, then we hope level.
But my question was about the hardware. So I'm sure that the crypto can handle.
Yeah.
But the hardware to have the ability to kind of...
Well, the design covers, as I understand, the three...
all the parameters.
So when you say the design, I'm trying to understand, is that, what do you mean by the design cover? So I'm sure that your design can be adapted to different parameters. But once I put my hardware out, I'm done. So my question is about hardware. It's not about the
scheme itself.
I would like a piece of hardware that if I run in the field for 10 years and in year 3 I learned that I have to double my W, I can issue a software update or a firmware update and I'm done.
So in terms of FPGA, the reconfigurability is easier, so relatively easier. So you can regenerate, like reprogram. So based on the newer parameters, you can generate the newer design, the new bit stream for the design, and that should work. It's relatively easier. In terms of when we are implementing an ASIC design, this is already taken into consideration, and we try to do it in a way that it supports all the parameter sets at runtime. So we need not go back and then change the design. So moving on to the next work that we've been looking into is some more side channel attacks on HQC. This is an ongoing work, so I'll try to be very brief about this. So here we are trying to explore some power side channel attacks on HQC, and this is based on one of the recent works from Beckwith et al., which proposed correlation power analysis on variable shifter, which we similar to what we use in our design. So we can mount. Using this attack, we can mount the attack on the decryption part at the polynomial multiplication variable shifter, and we will be able to potentially we should be able to recover part of the secret key. And the way the attack works is that the sparse polynomial is unknown, and that's the secret key, and the attacker controls the non-sparse polynomial, that is the ciphertext. And each time, each time we start the operation, as soon as the first index comes into the picture for the variable shift, the attacker observes the right address to the right address to the memory inside. The offset of where we start writing gives the information about what might be the index. And once we have that offset, we know how shifted are the indices from the point of the known ciphertext. And from then and on, the attacker starts observing the read locations to understand what are the forthcoming indices that would be coming out. So that way they are able to recover the overall. So at this point, we've started working on just the polynomial multiplication part, and we have been fairly successful in that. But the future work on this is to have the attack done on the HQC. And we are going to explore some of the countermeasures, and which are combination, like there are both. One is masking, which is quite popular technique, but it is expensive in terms of overall hardware utilization, because pretty much you're literally making another copy of the design to run in parallel. Other than that, there are more cheaper options like shuffling. Like each time that we are dealing with new ciphertext, we would shuffle the indices, and that will give some difficulty for the attacker to observe the traces. And same thing with shifting as well. For each iteration, the sparse polynomial is offset by certain point, and then it is shifted back after the operation. So all in all, in summary, what we saw today was some of the design aspects in terms of both performance as well as implementation security aspects of HQC. And as I mentioned, further research is required in terms of side channel analysis. And also to summarize some more work that we've been doing in terms of hardware implementations. I had opportunity to work on 6 schemes, and one among them is Frodochem, and that was my project during my time here at MSR. So yeah, with that, that concludes my talk, and thank you very much. I'll be happy to answer any questions.